Hello guys, so here's the next question for the problem of the day in the Leetcode. Okay, so the question name is count the number of complete components. So this question is basically from the graph. Okay, so if you know the implementation of graph, then you can basically do it, the question. And let's just not waste the time in reading the question. I will make you understand the question. Okay, so what we have to do, basically the two words that we are going to focus on is complete components. Okay, so in graph, what means complete component? So simply the basically complete component, the like this, if we take this example, this graph is a complete component. How? So basically from this edge we can reach every edge of this graph, like this and this. Okay, and from this also we can reach every edge. Okay, and from this graph is also we can reach every edge, and this is basically a undirected graph, so both direction is valid. Okay, and this is also complete component because from this is a symbol for node, so we can reach to themselves. Okay, so simply it is also a complete component. Okay, so you got it. Okay, what is complete component? So the two words that is mean is this component and complete component. Let's make just one map, another graph like it. Okay, so like this. Okay, so let's just assume that this is just connected to this, and this connected to this, and this connected to this, and this connected to this. Okay, so if you think, is this a complete component? This is a component graph basically. If you see that component graph is like connected, all edges are connected. Okay, no gaps is there. Okay, so it is a component graph, but it is not a complete component graph, because if you see that we can from here, okay, from here we can only reach here and here. Okay, but we can't reach here, and from here also we can reach here. So from every basically node we can reach only two nodes. Okay, so if this is also joined like this, okay, and this also, then it would be a complete component graph. Okay, from every edge we can reach any basically from every edge we can reach every edge. Okay, like from here we can reach this, and this. Okay, and from here also this, and this, all the edges we can reach. Okay, so you got the thing that what is complete component graph. Okay, so that's the main question. We have given graphs and we have to basically count the number of complete component graphs that it holds. Okay, so simply like in this question, this is example first, so you will simply return 3 because all 3 graphs are complete component. Okay, so simply the output would be 3, and you can see the output is 3. So if just think this edge was not there, the simply answer would be 2, because this will not be a component graph, complete component graph. Okay, answer would be 2, only these two. Okay, so you got the thing. Okay, so how basically we are gonna do it? Okay, so for graph you need to basically know the main implementation and basic graph things like okay, I am not gonna explain from basic. Okay, so you should know that. Okay, so let's just see. So graphs are basically implemented. Let's just take this example, this 3 example. Okay, so this is the graph I am choosing. Okay, so let's just take the number 0, 1 and 2. Okay, so if you see that how basically we are going to do this question. Okay, so there is many way you can use PFS, TFS, and other basically type of like union. Okay, so we are going to use basically adjacency method, okay, to do this. So we are going to make basically graph is represented in the form of adjacency list. Okay, so how basically that works? Okay, simply what we do is we write we take the array. So for every Okay, these are three vertices of this. Okay, and this will simply represent, this will take three list, adjacent matrix and adjacent list are the two ways which can represent simply the graph. Okay, so this can simply take a list of the 0 and this the total edges, basically total neighbor component that nodes that are added. Okay, so like for 0, let's just take here 0. Okay, and let's just take here 1. Okay, let's just take it here 2, and 0 is basically involved with 0 neighbors are 1 and 2, and if you see 1, the neighbors are 0 and 2. Okay, and if you see 2, then neighbors are 1 comma 0. Okay, so you got it. And one more thing, if you see in complete component, the self, basically the itself, the node, okay, the node itself is also its neighbor. Okay, or you can say, we can simply write here also 0. Okay, that's never. Okay, and we can also write 1, because it's the node itself is also its neighbor, or you can say it is also participating in complete component. Okay, so you can see these are the, okay, and if you can see that if these are complete component, then these, basically these are totally equal. Okay, you can see 0 1 2 1 0 2 2 1 0. Okay, you got it. These are all equal to it itself. Okay, so if these are complete component, then these list or the we will see how we are going to represent, but these are equal. The nodes, that the neighbor of nodes are all equal. Okay, if we sort it, let's just sort this. Okay, if we just sort it, then simply this will be equals to the same, all three would be equal. Okay, okay, the all three would be equal. Then we can simply return that total, we can simply count how many basically there are completed components. Okay, so basically this is the idea how we are basically going to do this. Basically first we are going to create this adjacency list, okay, of this graph, and then we are going to use hash map to store all these basically neighbors or nodes that are basically in this form of string. Okay, we will store so form of string and in this sorted order. Okay, sorted order. Then we are going to basically in map we are going to take the frequency of this. Okay, okay, so if this frequency, like the frequency would be simply 3, and the in graph the total number of nodes are also 3. Okay, then we are going to simply say that completed component is 1, so the one completed component is formed. Okay, so if just think this is also a graph, and simply it's like just take it, if we take it that 5, okay, 5 would be simply 5. Okay, simply there will be only one graph, then simply we will simply store this in also in hash map, and this also will have 1. Okay, frequency would be simply 1, and graphs node is also 1. Okay, and frequency is also 1, so simply it's also a completed component. Okay, so simply you got the thing how basically we are going to approach this question. Okay, so we are going to simply create a adjacency list to basically represent this graph in a form of basic graph, and then simply we are going to use this basically list or these neighbors that that we have calculated. Simply we are going to sort them and then put them in basically hash map in the form of string, and then we are simply gonna uh, basically take out the frequency, total number of times they are basically for every node. Okay, they are present for every node, so simply here it is 3. So if it is total number of like the total number of nodes that are present are equals to the total number of neighbors that are present, that is 3 and 3. Okay, then simply it is a completed component. Okay, so that's the approach. Let's just see the code, and we will see, I will provide you the code. Okay, Okay, so you can see the Leetcode. Okay, so here's the code. So let's just see. So first I have taken this 2D graph. Okay, that is simply one basically at every basically element will store the list of the neighbors. Okay, so you can see basically at every edge, or you can say at every index. Okay, so we have taken this map. Okay, that will simply take the frequency of the how many times the same neighbor cells appeared. Okay, then simply we can we have just first in basically initialize the graph with that is same element. Okay, that is we have seen that the its first vertices would be same. That is if zero, if this is zero, then its neighbor is zero also. Okay, then simply we have make this the neighbors, that is if 0 has neighbors 1 and 2, then this is the code for writing that. Okay, then simply we have simply check that if then we have just taken the neighbors, that is simply from graph. Okay, and then we have simply sort them. Okay, and then simply we have add them in the component in this map. Okay, and then simply we have updated the frequency. Okay, then simply we are going to what we are going to do is then simply we are going to check for every element in the this frequency, that is entry is the every key in the complete frequency. Okay, if the basically we have just added with comma, so we are going to count the commas. Okay, in the string, so that how many elements are there. Okay, so like here 0 has 0 comma 1 comma 2. Okay, neighbors, so we are going to count the commas. Okay, so simply that way we will get this number of elements, that is 3 are present. Okay, so after every element we have just added comma. Okay, 0 comma 1 comma 2 comma. Okay, then simply it will we have this use this comma count. Okay, so simply it will simply count the commas. Okay, total, and then simply if it is equals to size of the entry dot second. Okay, so if the both are equal, then simply we will update the complete component. Okay, key pair have basically both are equal. Okay, so number of nodes and number of neighbors are equal, that basically we are going to say, and we are going to at last return completed component. Okay, so let's just submit it. And you can see time complexity also, pick up and login. Okay, so that's